Let's do a couple more examples where we're looking at counting specific atoms or specific groups of atoms, such as a water molecule and a hydrate, when we have more than one molecule of the whole compound. So I'm going to do two more examples that are a little bit more challenging. And in both of these examples, I will work through it looking at a simple mathematical way to solve the question. And the reason why I will do that is to help you develop a good conceptual understanding of what you're doing. And I'm also going to solve the same question using a conversion factor. And the reason why I'll do that is because later in this unit we're going to be solving more complicated calculations that involve more than one conversion, and we're going to want to use conversion factors. So starting to think now about how can I use a conversion factor to solve this question is going to really help you out down the road. Let's go ahead and do two questions together. So here's the first question. How many hydrogen atoms in 6.5 times 10 to the 17 molecules of ammonium phosphate? Okay, so earlier on in this lesson we had to calculate how many hydrogen atoms were in one molecule of this compound. Now we want to know, well, what if we have more than one molecule? What if we have 6.5 times 10 to the 17 molecules, which is a much more realistic number, where in chemistry we're usually dealing with really, really large numbers of molecules. So let's go ahead and solve this question together. Okay, so first of all, I'm interested in hydrogen atoms, and that's really important. So when I look at this compound, I'm only concerned with the number of hydrogen atoms that I have. And our first step is we're going to count how many hydrogen atoms are in one molecule, and once we know that, then we can figure out how many are in this number, 6.5 times 10 to the 17 molecules. So that's our first step. We're going to find out how many H atoms are in one molecule. So at this point we should be able to do this pretty quickly, and I'm going to have a look at this, and I'm going to do it without a lot of writing here. I see that I've got the H inside the brackets here. There's 4 hydrogen atoms in one NH4 ion, okay, and then I've also got this 3 outside the brackets. So in total I have 3 times 4 hydrogen atoms inside one molecule. So let's write that out. One molecule, so one molecule of the whole compound is equal to 12 hydrogen atoms. Okay, so this simple mathematical way to solve this, if all I'm being asked for is how many hydrogen atoms are in 6.5 times 10 to the 17 molecules, is to simply go ahead and multiply 12 by the number of molecules. Right? We know how many hydrogen atoms are in one molecule, so if I've got more than one, I can just multiply the number of hydrogen atoms by the number of molecules that I have. So that's the really simple mathematical way. So the number of hydrogen atoms are going to be equal to 12, because that's how many hydrogen atoms are in one molecule, times the number of molecules that I have. So I've got 6.5 times 10 to the exponent 17, and my answer here is going to come out to be 7.8 times 10 to the exponent 18, and my units are atoms, because I'm talking about hydrogen atoms, and I always want to have my units in my answer. Alright, so that's a quick and easy way to solve this. The reason I'm solving it like this is just for us to think about why are we getting this number, and have a good understanding of where that's coming from. Okay, now we could actually solve this exact same question using a conversion factor, and I've already written the conversion factor out right here. So the fact that there are 12 hydrogen atoms in one molecule, that could be written as a statement, or it can be written as a conversion statement like this. One molecule equals 12 hydrogen atoms. When you write it like that, this can quickly be made into a conversion factor when we put it into a calculation. So let's do the exact same question here. We're going to solve it again, but this time, instead of using the simple math method that I did right here, I am going to use a conversion factor. Okay? And so it looks like this. And this is going back to Unit 2, where we said what we want is equal to what we have times what we know. Okay, and what we know is this right here. This is what we know, our conversion factor. Okay, that's a conversion factor that can be written like a ratio. Okay, so the number of hydrogen atoms here is what we have, which are 6.5 times 10 to the 17. Now I'm going to put my units in here. That's molecules. So if I start with this many molecules and I want to know how many hydrogen atoms I have, I can simply use a conversion factor to convert from molecules to hydrogen atoms. So I'm going to take my statement right here and I'm going to divide it right down the middle where I've got the equal sign, and because I'm trying to cancel out of molecules, I'm going to put my one molecule on the bottom. And I'm going to put the other half of the conversion factor, 12 hydrogen atoms, on the top. And right away, I want to cross out or cancel out of any units that I can cancel. So I'm canceling out of molecules here. Molecules divided by molecules. I'm left with hydrogen atoms, which is what I wanted, and I'm ready to go. So my answer is 6.5 times 10 to the 17 times 12, and my answer is 7.8. Sorry, 7. So 7.8 times 10 to the exponent 18, and my units are atoms. And I can check for Sig Figs. 2 Sig Figs in my original question, 2 Sig Figs allowed in my answer, and so I'm good. I have the right number of Sig Figs in my answer. So really, it's the exact same way of solving it. It looks a little more complicated to use a conversion factor, and you might say, oh, why would I do that? I could just do it so quickly in my head or with my calculator. And the only reason why we would want to use a conversion factor is because later on we're going to get into more complicated calculations, as I mentioned, where we will be expected to use a conversion factor. So if you start using them now, it just makes it that much easier down the road to continue to use them. Let's do another example. Okay, here I've got how many water molecules in 7.3 times 10 to the 35 molecules of the hydrate copper sulfate pentahydrate. Okay, so the hydrate is this guy right here, and I'm just interested right now in how many water molecules. So the water molecules are right here, and in one molecule of the hydrate there are 5 water molecules. So I'm going to write that out, but I'm going to write it out now as a conversion statement with an equal sign that I can quickly and easily turn into a conversion factor. So it looks like this. I could say 1 molecule. If you want to be really specific, you could write 1 molecule of hydrate. Okay, I'm going to keep it a little bit simple here. 1 molecule is equal to 5 water molecules. So 1 molecule of hydrate is equal to 5 water molecules. So I've just done the first step, which is to count how many specific groups of atoms, in this case a water molecule, are in 1 molecule of the compound. The next step then is to figure out how many we have if we've got more than 1 molecule. So we've got 7.3 times 10 to the 35 molecules. So a quick and easy mathematical method here would be just to take this number, 7.3 times 10 to the 35, and multiply it by 5. Okay, that's going to tell you how many water molecules are in that many molecules of the hydrate. If I want to use a conversion factor, which is a really good habit, it would look like this. Okay, so I'd say the number of water molecules, which is what I want, is equal to what I have, which is 7.3 times 10 to the exponent 35 molecules of the hydrate. I'll write the whole word, molecules. Okay, times what I know. Now what I know is this conversion factor right here. So by writing it out like an equal statement, it makes it really easy to put into my calculation as a conversion factor. So I want to cancel out of molecules of hydrate, so I'm going to put that one molecule on the bottom of my conversion factor. And I'm going to put the 5 H2O molecules on the top. And again, right away we want to cancel units that we can cancel. And so molecules are going to cancel, and I'm left with water molecules. And so my answer, 7.3 times 10 to the 35 times 5, comes out as 3.65 times 10 to the 36. And we always want to have units, so the units here are molecules. You could also write water molecules, would be totally acceptable. But before I finish, I want to look at sig figs, and I only had 2 sig figs to start with in my question. So I have to limit my answer to 2 sig figs as well, because this was a multiplication division question. So I'm going to round up that 6 to a 7, because the number 5 will round it up. And so I have 3.7 times 10 to the exponent 36 molecules. Always including units in my answer whenever there are units. And 2 sig figs is the correct number of significant figures in my answer as well. And there we go.